Welcome to Study Loop.
Welcome to a new problem. This time we have a plane that's flying in a specific direction and it's being affected by multiple forces. For example, it's being lifted up, and there's also this is a lift, and then there's a drag on the plane. On top of that, the air is pushing up the wings. So this is the force of the air on the wings. And there are a couple of things that stand out in this problem. For example, air resistance is proportional. Air resistance is proportional to the square of the velocity of the plane. And the wings also provide some resistance. Remember, air flows through the wings. So if this is a wing, you're going to have some air flowing on top of the wing, and it does something. It goes slightly forward, and the it goes forward, and then it's pushed downwards. So if this is the wing, this is the plane. The air flows through the wings, and then it's pushed downwards. And according to Newton's third law, action and reaction forces are equal in the opposite. And so this action of being pushed down, it's going to force the wings to be lifted upwards. And that's what you want, because you want to raise the plane, but then the outcome of that process, the outcome of um, the air flowing through the wings, means that you have a backward induced drag. So as this one goes forward like that and then down, and then you have this drag going backwards like that, we call this an induced drag, because of the air in the wing, and it's inversely proportional to the velocity squared. So if you look at those two aspects of the air resistance and the wing resistance, there is a force that comes up responsible for these two actions, this action right here and this action right here. And that force is modeled by alpha v squared plus beta over v squared. Remember, alpha for a Cessna plane, for example, Cessna 150, the alpha happens to be a 0.30 Newton second squared over meter squared, and then the beta happens to be, so this is just specific for the Cessna. Other planes will definitely have different types of numbers, constants, but in general, this is what happens. So there are two things we're looking at in this problem. The first part is that we're going to transform things in kilometers per hour. We want to get the maximum range of the plane. And then the second part is we want to get the maximum endurance of the plane. Another way of thinking about the maximum range of the plane is to imagine the uh, maximum velocity. Maximum velocity. So maximum velocity will mean maximum range. And then maximum endurance will mean maximum time. So those are the two things happening in this problem. So in the next page, we first of all get to look at the maximum range, and the maximum range is going to happen when we have the force. This is part A. We have the force that we're dealing with, force air, that's given as equivalent to alpha v squared plus beta over v squared. At maximum range, the derivative of this force with respect to velocity um, becomes equal to 0. So if you do the derivative, you bring the 2 down. This is 2 alpha v plus 2 beta over v. So that derivative equals to 0. And we can solve. Actually, this is v cubed. Sorry, this is v cubed. We have to change some numbers a little bit. This is v cubed. We're doing the derivative. Remember, it's when it's down, it's negative. Because this is like this. Just to explain what happens with the v squared. This v squared is the same as v negative 2. It comes down, it's going to be negative, and then plus uh, minus 1. Sorry. So you have negative v negative 3, which is the same as negative 1 over v3, and that's what we have here. And so since it's 0, we're going to solve for v. And so we have 2 alpha v equals to 2 beta v cubed. Cross multiply both sides by v cubed. We get 2 alpha v to the 4th power equals to 2 beta. And we want to solve for this v, so we have to divide both sides by 2 alpha. And so v happens to be 2 beta over 2 alpha raised to 1/4. Now, the reason why we are interested in the maximum speed, because the maximum speed gives us the maximum range. So we can make that statement here, that getting the maximum speed of velocity means that we have the max range. It's the same thing. So if we solve for that, we plug in the numbers. We have 2 times beta. Beta happens to be just to make sure we had the right numbers. Beta happens to be so these 2's canceled out, so we don't have to hold on to those 2's. They're gone. So we're only interested now in beta and alpha. Beta is 3.5 times 10 to the 5 Newton meter squared, s squared, all over 0. So I'm looking at these numbers. Beta is given as 3.5 times 10 to the 5, and then alpha is given as 0.30 Newton second squared, 0.30 Newton second squared meter squared, and all of that is raised to 1/4 power. And then when we simplify that, when we simplify this, we end up with the solution in meters per second, which is approximately 33 meters per second. If you want to change that to kilometers per hour, you have to multiply by 18/5 kilometers per hour. And so that's approximately 118 kilometers per hour. That's the speed of the Cessna or the plane at maximum range. To get the maximum time endurance, we're going to go to the next part. So this is part B. Maximum endurance. Maximum endurance happens during maximum time. And you want to think about power, dp over dv equals to 0. That's when we have the maximum endurance. And remember, power is the same as the force times the velocity, dot product. So this is not time derivative, but velocity derivative of force and velocity of product. And so it's the same as saying velocity derivative. The force that we are using, if you go back, it's the same as this for the force in the air, this one right here, alpha v squared plus beta v, alpha v squared plus beta alpha v squared, just to make sure we have the right force. Alpha v squared, this is alpha v squared plus beta over v squared also, and then it's multiplied by this v. So this is the force and this is that velocity. So we're doing the derivative of a distributive property, bringing in this velocity inside. We have alpha v cubed plus beta over v, because this v is going to cancel one of these v's. So if we get the derivative of that, we see that it happens to be equivalent to 3 alpha v squared plus, actually not plus but minus. We're doing the derivative. So if we have this v right here, it's going to give us a minus right there, and then we have b over v squared. In the next page, we end up with 3 alpha v squared minus b over v squared equals to 0. So we simplify that. We move 1 to the other side. So 3v squared equals to b over v squared. We want to solve for v. So we cross multiply by v squared. We get 3 alpha v to the 4th power equals to beta. And then we divide both sides by 3 alpha. And so v to the 4th power is beta over 3 alpha. We simplify the v by getting the 4th root on both sides. So b over 3 alpha, like that. And then now all we have to do is plug in the numbers. Remember, beta happens to be 3.5 times 10 to the 5 Newton meters squared over s squared. This is s squared, just recall. So 3.5 times 10 to the 5 Newton meters squared over s squared, all over 3, this 3 times alpha, which is 0.30 Newton second squared over meter squared. So if you do the math for this problem, you're going to see that you end up getting approximately 25 meters per second. For this one, you can change that to kilometers per hour by multiplying by 18 over 5 kilometers per hour, because remember, this is equivalent to 1 meters per second. So you get approximately 90 kilometers per hour. So this is the whole process of finding the maximum endurance. So the maximum endurance happens, we'll say max endurance happens at v equals to 90 kilometers per hour. Okay, so we found those two values that we wanted. The first value, as you can see, was the this one right here. That's the speed at the maximum range. When does the maximum range happen? And then the other one would be when does the maximum endurance happen? So right there. Okay, thank you very much for watching the video. I hope you enjoyed it. Feel free to ask any questions, and hope you also have a wonderful day. Okay, thanks. Bye.